Okay, we're going to look at amides and amino acids, mainly amides. So the general formula, we can have primary or secondary amides, and the naming actually, we'll just look at a diagram in a sec, don't worry about this too much right now. The naming is something anamide, so for example, methanamide, ethanamide, and so on. So let's just look at some examples. This is a primary amide. It has the amino group on the end. So that's the carbonyl group with the NH2 attached to that same carbon. So this would be propanamide. This would be a primary amide because it has the amide functional group on the end. We can have a secondary amide and even a tertiary amide. So here what we have is we have an alkyl group attached to the nitrogen. So we've got our propanamide, which is this part here, propanamide, and then we've got ethyl attached, an ethyl group attached to the nitrogen. So we write that as N-ethyl propanamide. N-ethyl because the ethyl group is attached to the nitrogen. So N-ethyl propanamide, the propanamide is this part here. And imagine if we had a different alkyl chain down here, that would be a tertiary amide. Okay, the physical properties. Methanamide is a liquid at room temperature. All the other amides are white crystalline solids at room temperature. Because of the hydrogen bonding, in fact, you get like it's kind of like with carboxylic acids, you get like a double hydrogen bonding situation going on. We get a high melting and boiling point for amides, and they're soluble in water, but as the carbon chain gets longer, the non-polar part becomes more significant and becomes less soluble in water. So here's what I was talking about with the hydrogen bonding. We have, excuse me, we have hydrogen bonded to in a covalent bond with a highly electronegative nitrogen atom. The electrons in the bond are pulled away from the hydrogen, leaving an exposed nucleus, which is attracted to the lone pairs of electrons on the oxygen atoms. And so we can get between a pair of amide molecules, we can have two hydrogen bonds existing, just the same as we do for carboxylic acids. Okay, we're going to look at these reactions: preparation, hydrolysis, and polymerization. So the preferred method of preparation of an amide is reacting an acid chloride with an amine, or ammonia in this case. We can also do it by reacting an ester with an amine or ammonia. So what happens is if we react an acid chloride with ammonia, we're basically replacing the Cl with an NH2. And we're getting HCl as a byproduct. If we're reacting an ester with ammonia or an amine, what we're doing is we're basically cutting off the molecule here and adding NH2 to it. So we're cutting it off here and adding NH2, and then this part here we're adding a hydrogen, and this R dash, this alkyl group here forms the alcohol. So you get an alcohol as well as an amide. Another way is by reacting a carboxylic acid with an amine or ammonia. We get a carboxylate salt, in this case ammonium ethanoate, and then the thermal decomposition of that salt produces an amide, a primary amide in this case, because we're reacting with ammonia. Okay, the hydrolysis in acidic conditions, which is where we're reacting with hydronium ions, we get a carboxylic acid and the ammonium ion. Reacting in hydrolysis in alkaline conditions, for example with sodium hydroxide, we get a carboxylate ion, so in this case the ethanoate ion and ammonia. So ammonium ion, ammonia solution. We can form polymers using amides. We can form a polyamide by reacting, in this case, a diamine. So that's an amine or a hydrocarbon which has an amino group at both ends, with a dicarboxylic acid, which is a hydrocarbon that has a carboxyl group at both ends of the molecule. And the carboxyl group reacts with the amino group. We get water taken out as a byproduct, and the bond forms between this carbon and this nitrogen. So we end up getting, this is an example of nylon. We've got the nitrogen, the alkyl chain, first alkyl chain here and nitrogen here, that's what we've got up here. That joins on to this carbon, and then we've got a carbonyl group, another alkyl group, and another carbonyl, and then this whole section is what repeats again and again. Now it's not shown here, but try and imagine that the next thing after this carbon is an NH. So this here is the next thing that comes after this. And that little group, that CONH, is known as a peptide link or an amide link. Same thing, peptide link, amide link. Or you might hear it called a peptide bond or an amide bond, so you know what that word means when you come across it. It's the link formed, it's an amide link that exists in a molecule or a polymer. Okay, so that's amides. Now let's have a look at amino acids. Amino acids contain two different functional groups. They contain an amino group and a carboxylic acid group, hence the name, amino acids. Amino because they have an amine group, and acids because they are a carboxylic acid. The carboxylic acid group has a higher priority than the amine group, so they're considered acids with an amino group rather than the other way around. Rather than being amines with the carboxyl group, what they are is acids, and they have an amino group. The naming is amino something enoic acid. So, for example, this one here, amino ethanoic acid. So it's ethanoic acid with an amino group on the second carbon atom. This is the first carbon atom of the carboxyl group, and this is the second carbon atom. This is also known as glycine. Alanine is another one. So we've got two amino propanoic acid. Okay, propanoic acid we can see here. This is propanoic acid, and it's got an amino group on the second carbon. That's alanine. All amino acids except for glycine are optical isomers. We can see that here, right? If you look at this carbon here, this is a chiral carbon atom. It has 1, 2, 3, 4 different things attached to it. Whereas in glycine, the carbon only has, it has two of the same, right? It has two hydrogens attached to it, so it's not multiple optically active molecule. Okay, so interesting thing with amino acids is that they contain an acidic group and a basic group. Now let's go back to our diagrams. The carboxylic acid group here is an acidic group, an acidic functional group, but the amino group is a basic functional group. So they behave as both an acid and a base. The carboxyl group tends to lose hydrogen ions, it's a proton donor, and the amine group tends to gain hydrogen ions, it's a proton acceptor. And we call this a Zwitter ion, so it's an ion that contains a positive and a negative charge at the same time. The fact that amino acids are Zwitter ions give reason to their physical properties, the fact that they're very soluble in water, and solids at room temperature, a high melting point, and strong intermolecular bonds. This is just to show it diagrammatically. This is basic, this is acidic, this accepts protons, and this, this is a proton acceptor. Let's go back. No, proton donor, sorry. So this part is a proton donor, it gives away a hydrogen ion. This part is a proton acceptor, it accepts a hydrogen ion. Okay, and that's amino acids and amides.